Today we're going to introduce the basics of logistic regression.
This space shuttle dataset is based on Chapter 7 from the textbook Practicing Statistics.
In this example, we have 24 flight numbers. You can see a few of them here, the dates in which they were launched, the air temperature at the time of the launch, and if there was any indication of whether there was O-ring failure during the launch. Based on the case study in the textbook, our primary question of interest is whether ambient temperature helps us predict whether a launch is successful. However, in logistic regression, the response is categorical, not quantitative. In this dataset, we only have two options for the response variable: 1 if the launch was successful, and 0 if the launch was not successful. We could try to fit a straight line using simple linear regression to this data, but clearly there's some problems. Although the simple linear regression model does indicate that when temperatures are higher, you're more likely to have a successful launch, the line gives very little indication of what your expected response should be. In addition, in trying to predict the probability of a successful launch, the simple linear regression line goes above 1 and below 0, which clearly is not possible when we're talking about probabilities. So instead, we create a logistic regression model. And as you can see in this graph, a logistic regression has a characteristic S-shaped curve that ranges between 0 and 1. The logistic regression model can be written with the following form. One thing that often gets missed when people are introducing logistic regression model is that logistic regression is just one form of a generalized linear model. It's important to recognize that logistic regression is not simply just transforming the response variable, as we've sometimes seen in simple linear regression models, in order to get a different shape or a different pattern. We actually use very different techniques to estimate the B0 and B1 variables. All general linear models have three components. They have a linear predictor component. You notice here, this looks exactly like what we would see in linear regression. The linear predictor in any generalized linear model can include many explanatory variables, including indicator variables and interaction terms, as well as other transform variables. Generalized linear models also include a random component, or an error term, that is assumed to be independent. However, in generalized linear models, the error terms are not required to follow the normal distribution. In addition, generalized linear models do not require that the variability of the error terms need to be constant. You may recall in simple linear regression, we require the error term to be constant and normally distributed in order to conduct hypothesis tests. Since these assumptions are violated for any logistic regression or generalized linear model, we will need to use new techniques for statistical inference.
Instead of using least squares estimates to estimate beta naught and beta 1, we will now need to use maximum likelihood estimates. These are actually based on an iterative technique and really cannot be done by hand, so we use software to calculate maximum likelihood estimates in logistic regression.
Finally, generalized linear models have something called a link function. A link function is the function that fits the expected response to a linear predictor. In this case, our link function is called the log odds function, or the logit function. There are certainly many transformations or many functions that could create an S-shaped pattern. Any link function in generalized linear models depends on the distribution of the response variable. In logistic regression, the response variable is binary. Other link functions for binary response variables do exist, but the log odds, or the logit function, is the most common because it's the easiest to interpret. It's important to recognize that this model may look slightly different depending on how it's presented. Here, we are using parameters, pi, beta naught, beta 1, and epsilon, representing the true unknown population data. Often, instead, you will see a model like this, where we have a B0 and a B1 that we've calculated. The B1 is a maximum likelihood estimate of beta 1, and the B0 is the maximum likelihood estimate of beta naught. And again, pi hat is the estimate of pi. With a little algebra, for example, taking the exponent of both sides and solving for pi, we get a mathematically equivalent statement, but in terms of predicting y hat. While this model might look a little strange, it still does have some characteristics that are fairly easy to understand. Changing B0 shifts the logistic regression model to the right or to the left, and adjusting B1 will have an impact on the steepness of our S-shaped curve. In addition, when b1 is negative, the slope will be negative in the logistic regression model. In this video, we presented a quick summary of what the logistic regression model is. In the next video, we will talk about how to use statistical inference and interpret the log odds using logistic regression.